Hello and welcome to eCampus. Today we are going to attempt Physics Cambridge IGCSE Paper 3, and this one is from May-June 2024 and variant number 2. So without further ado, let's start from question number 1. Alright, so question number 1, we have a speed-time graph where speed is on the y-axis and time is on the x-axis. And this is for a car traveling along a flat, straight road. So what do we have to do? All right, so we have to describe the motion of the car between time t0 and t 2 seconds. And as we look in this window, we see that the speed of the car is increasing at a uniform rate. Or in other words, we can say that the car is moving with uniform acceleration. Or we can also say that the rate of change of speed is constant, which all means the same thing. Moving down, we have to state the value of acceleration of the car between time 4 second and 8 second. All right, so between 4 second and 8 second, we see that the speed of the car is constant, or the car is moving with a constant velocity. Now, since the rate of change of velocity or the rate of change of speed is zero, then we can say that the object is moving with zero acceleration. So, since rate of change of speed is zero, therefore zero acceleration. Now calculate the distance traveled by the car between 8 and 14 seconds. All right. So we have to look in this bracket now 8 and 14 seconds, and we have to calculate the distance covered by the car in this time interval. Now, in order to find the distance from the speed time graph, we have to look at the area under the curve, which happens to be this right angle triangle as I'm highlighting here. So we have to find this area. All right, so roughly highlighted it. This happens to be a right angle triangle. And just a quick refresher, for a speed time graph, the area under the curve gives information about the distance covered, whereas the tangent or the gradient of the speed time graph gives us information about the acceleration, as we just saw in 1b. So from this information, we can find uh, the distance travel is equal to the area under the curve, which happens to be a right angle triangle, and we can find that through the formula of half. The base happens to be 14 minus 8 is 6 seconds multiplied by the height. How much is the height? It is 20 meter per second. Seconds would cancel out in seconds. 2 divided by 20 is 10. So 10 times 6 is 60 meters. So the car travels 60 meter between 8 and 14 seconds. All right, moving on. Question number 2. The student wants to find the volume of a piece of metal. The student can use any of the items of the equipment shown in figure 2.1. All right, so what do we need to do? Describe how the student can find the volume of the piece of metal by using equipment from 2.1. All right, so we have a measuring cylinder, some quantity of water in a beaker, and then we have a displacement can, and then the metal with an unknown volume. All right. It's pretty simple. We have attempted several times during our lab sessions. First, we would pour water in the measuring cylinder. Then we would take a reading or note down the level of water from the measuring cylinder. Afterwards, we would place the metal inside the mirroring cylinder. And when we place the metal inside the mirroring cylinder, the level of water would rise. And we would note or take reading of the change in level of the cylinder, mirroring cylinder. And finally, the delta X, or the change in level, corresponds to the volume of the metal. Or that's it. Moving on. The part B says the volume of a different piece of metal is 30 centimeter cube. The mass of this piece of metal is 192 grams. Calculate the density of metal and include the unit as well. All right, so different piece of metal is an examiner's way of saying that we have a different sample now, different sample from part 2A, and whose volume and mass is known to us. And we have to find the density of the metal. So it's a pretty straightforward question. It's simple, and we will simply use the formula of density. So density, which goes by this simple rho, is equal to mass per unit volume. And we don't need to convert it into any SI units because not specified. So simply 192 grams over 30 centimeter cube. So 192 by 30 gives us 6.4 gram per centimeter cube. So it is 6.4, and with the units of grams per centimeter cube. Moving on to question number 3. All right, so figure 3.1 shows two solid shapes, a cylinder and a cone, which are made from the same material. So that's important. The both of these objects are made with the same material. In part 3, we need to state and explain which shape is more stable. All right, so when we are talking about stability, the object which has a lower center of mass is more, or in other words, we would say that an object whose mass distribution is closer to its base or closer to ground is more stable. So among the two shapes, definitely cone is the one which is more stable. And as far as explanation is concerned, as I just said, uh, because center of mass is lower, or mass distribution is closer to base. Moving on to part B. The mass of the cylinder is 0.25 kilogram. Calculate the weight of the cylinder. All right. So, weight force can be found by multiplying mass with the gravitational acceleration. So, weight equals mass times gravitational acceleration. Now, we need to answer Newton. So, we're already given kilograms. So, 0.25 kilograms multiplied by 9.8 meter per second squared. So, the weight comes out as 2.45 newtons. All right, moving on to part C of the question. Now, a horizontal force of 3 Newton tilts the cone, and the cone balances on one edge as shown in figure 3.2. Calculate the moment of force of the 3 Newton force about the pivot. All right, so the moment of a force can be found by multiplying the magnitude of force with the perpendicular distance between the line of action of force and the pivot point. So the pivot point is already specified to us. We can extend the line of external force just to be consistent with our working. And the perpendicular distance is this one, which is already given to us. So moment of force is equal to the magnitude of force, which is 3 newtons, multiplied by the perpendicular distance, which happens to be 22 centimeter. Since we need to answer Newton centimeter, we just multiply the two things. That is 66 Newton centimeter. All right. So yes, we have a part two as well. Determine the moment of the weight of the cone about the pivot. Use ideas about the principle of moments. All right. Since the cone is in equilibrium, then we can say that there must be some other force that's balancing it, right? So that other force is the weight force, which is balancing it. And since there is no other force other than the 3 Newton force and the weight force, then we can say that the weight force would exhibit the same moment about the pivot point. However, its direction would be opposite. This 3 Newton force is creating a clockwise moment, and this weight force would create a counterclockwise moment. Although that's not needed, but just to be consistent with our understanding. So the moment of weight about pivot would be exactly the same, but just opposite in direction. Moving on to question number 4. So figure 4.1 shows a flow diagram for the energy transferred in a television. So that's total energy, some useful and some wasted. State two ways in which useful energy is transferred from the television. All right. So when we're talking about useful energy, we talk about the energy used in the intended purpose. All right. So for a television, one could be obviously the visuals uh, from the LED, or to be more specific, let's say the light from LED or CRT. And the other would be sound. All right. The sound coming out from a television, that's also one of the intended purpose, so that's useful as well. All right, then determine the value of the wasted energy output from the television. So total was 100, useful was 30, so waste would is definitely the difference between 100 and 30. So 70 joules is the wasted energy. That's pretty straightforward. All right, moving to part B of the question. So we have a reservoir here. It's a hydroelectric power station. Describe how a hydroelectric power station generates electrical power. So we can write in bullets. First of all, we have a reservoir with water at high gravitational potential. Then this water moves through the pipe, move down the pipe towards the power station, and as it moves down, its kinetic energy increases. This high energy water then drives the turbine. Turbine rotates the shaft of generator or the coils of generator, generating electricity. So that's comprehensive. That's it. Apart from cost, state one advantage and one disadvantage of generating electrical power using a hydroelectric power station compared to a coal-fired power station. All right, so there can be numerous advantages and disadvantages. We're going to stick to one. So one of the main advantage or the most significant one is that there are no carbon footprints. There are no carbon emission with the hydroelectric power plant. Other than that, we can also say that there is no biofuel involved in that. It's just it's completely renewable. The water from the water cycle, it just we use the water from higher potential and then just release it into the normal stream, and through the water cycle, just can again fills the reservoir. So there is no biofuel needed. Among the disadvantages that we need a very large area has to be filled with water. And obviously, people have to be relocated, and this whole habitat of that area has to be changed or modified. So that's one of the major disadvantages. Also, it takes a very large time to build, and then obviously, it is prone to it involves a lot of cost as well as compared to the coal-fired power station. So, but we're gonna stick to one. Are you struggling with IGCSEs or A-level physics? Don't worry. We are here to help you ace your exams. At eCampus, we specialize in physics tutoring for Cambridge International and Edexcel students across the globe. So whether it's nuclear physics, electromagnetism, quantum physics, or any other topic that you find complicated, our expert tutors with over 7 years of proven success make even the toughest concepts easier to understand. So what are you waiting for? Book your free demo lesson today and experience the difference for yourself. All right, moving on to question number 5. So figure 5.1 shows a metal block at room temperature on a table. Now describe the arrangement, separation, and motion of the particles in the metal block. All right, so since it's a solid metal, so the arrangement of molecules inside this metal would be fixed or lattice or a lattice structure. So particles arranged in fixed position. As far as separation is concerned, the separation is very, very smaller as compared to the arrangement of molecules in liquids or gases. Liquids, gases. And the motion of the particles only exhibit the vibrational motion and no translational kinetic energy whatsoever. All right, so coming on to part B1, the temperature of the metal block has decreased. Describe any changes in the motion and separation of the particles in the metal block. Now, the temperature is directly related to the total internal energy of the substance. Now, since the temperature has decreased, that means the internal energy has decreased. And therefore, the motion of the molecules, which was vibratory in nature initially, the magnitude of vibratory motion would decrease. And the separation of the particle, because the temperature is being decreased and the total energy is decreased, the separation of the particle would get even more cramped up than before. So separation would get even smaller. All right. A scientist then cools down the metal block and until its temperature is close to absolute zero. Describe the motion of the particles. Now, as I've just mentioned, that temperature is directly related to the total energy of the substance. And since that temperature is brought close to zero, therefore the energy of the substance is very, very small. And therefore the motion of the particle would be which was vibratory in nature because the substance is solid. The magnitude of the motion, the vibratory motion, would get even more smaller. Now, the weight of the metal block is 26 Newton, and the area in contact with the table is 42 centimeters square. Calculate the pressure on the table due to metal block. All right, so this is the arrangement. We need to find the pressure exerted by metal block onto the table. Uh, we know the definition. The pressure is force acting per normal cross section area. So force is known to us, and the arrangement of the metal block on the table is already like in normal position or perpendicular position. So the cross sectional area is also given. So 26 over 42, and we don't need to convert into any SI units because the answer has to be in Newton per centimeter squared. So 26 divided by 42 is 0.619. And to do significant figure, we can say 0.6 Newton per centimeter squared. Moving on to question number 6. A student studies different types of waves, and she studies waves on the surface of water in a ripple tank. The frequency of the waves is 4 hertz, and the wavelength is 5 centimeters. Calculate the speed of the waves. That's pretty straightforward as well. We know the formula for speed of the waves. We can find the wave speed as v equals frequency multiplied by the wavelength. Frequency is given as 4, and the wavelength is given as 5 centimeter, and that is 20 hertz is basically per second, so centimeter per second. Moving on to part B of the question. The student puts a block into the ripple as shown in figure 6.1. All right, so the block sinks, the wave travel towards the block and then over the block. State and explain what happens to the waves as they travel over the edge of the block. So it's a 3-mark question. So one thing we see right off is that the spacing between those parallel lines, which happens to be wavefront, they decrease in magnitude, they decrease in size. So that's an indicator that the wavelength or lambda, it has decreased. Further, we also see that there is some refraction because of this part. There is some refraction as the wave enter from uh, deeper water to shallower water. Also, we see that the direction of wavefront changes. You see, initially it was this direction, then the direction uh, is skewed a bit. All right, let's move on to part C of the question. Uh, the chart in figure 6.2 shows the main region of the electromagnetic spectrum. All right, state the name of one region that has longer wavelengths than visible light. So we know that the spectra to the left visible light contains higher wavelengths or lower energy. So we can name any of them: radio waves, microwaves, or infrared. Let's say radio waves because it has least energy or maximum wavelength of the electromagnetic spectrum. Now describe one use of UV radiations. We can say one use could be to sterilize food, or we can also say another use could be to highlight defects in currency notes or to identify forged currency notes. Now, moving on to part 3, compare the speed of radio waves with the speed of gamma rays as they both travel through a vacuum. All right. So radio waves and gamma rays both are electromagnetic waves, and electromagnetic waves exhibit same speed as long as it's moving in the same medium. All right, so its speed would be the same because both are EM waves and moving in the same medium. Move on to question number 7. So we have a circuit here. A battery, a lamp, and a fixed resistor and a switch are connected. All right, so in question 7a, the potential difference across the lamp is 48 volts. All right, and the current in the lamp is 0.4 amperes. Calculate the resistance of the lamp. All right, so when finding the resistance of the lamp, we will employ Ohm's law, and from Ohm's law we can say that V equals IR, and the resistance can be found as uh, voltage across the lamp over current through the lamp. So we are given that the voltage across the lamp is 4.8 volts and the current through the lamp is 0.40 amperes, which gives us 12 ohm resistance. Moving on to part B, state and explain how closing switch S affects the brightness of lamp L. All right. So when the switch S is closed, now the effective resistance of this whole part, because the resistance R and the resistance of this wire S would be in parallel, the equivalent resistance of this whole parallel circuit would be lesser than the resistance of the wire. So the overall resistance of the circuit would be decreased, and therefore the voltage drop across this resistance, if I mark that in red, the voltage drop across this equivalent resistance would be lower, and now more voltage would be dissipated across the lamp, and therefore the lamp should shine brighter. So let's write that down. Now closing switch makes a wire parallel to resistor R, and the equivalent resistance would become less than the resistance of wire. More voltage would be dissipated across lamp, and therefore more current would pass through lamp, making it shine brighter. All right, that's comprehensive. Let's move on to question number 8. All right, so the battery in a laptop computer is connected to a battery charger for 20 minutes. The potential difference across the battery is 14 volts. The current is in the battery is 1.8 amperes. So there are some details. Um, and it is assumed that while connected to the battery charger, this is the steady state voltage and the current. All right. So calculate the energy transfer to the battery in 20 minutes. Again, the assumption that this voltage and this current was there for the last 20 minutes, we try to calculate the energy transfer. So first of all, let's find the power, uh, because energy is power multiplied by time. So the power, or the instantaneous power, would be equal to voltage multiplied by the current. So that is 14 multiplied by 1.8. That is 25.2 watts. And since we want to find the energy transferred in 20 minutes, we multiplied 25.2 watts, 25.2 watts with 20 multiplied by 60 seconds. So it's 30,240 joules. All right, moving on to part B. The battery charger includes a transformer, shows the transformer input voltage to 40 volts and output. And yes, we have some primary and secondary coil identified. State the name of materials used for the core of the transformer. So the core of the transformer should be made with a ferromagnetic material. And the name, we can call that iron, one of the ferromagnetic materials, soft iron. For part 2, the transformer has 4800 turns on the primary coil. We call that NP. And calculate the number of turns on the secondary coil. We call that NS, which is to be found out. All right. So we also know the input voltage and output voltage. We call that VP because this is the voltage in the primary coil, and we call that VS because the voltage on the secondary coil. So from the turns ratio formula, we can say that NP over NS is equal to VP over Vs. We know all these things, number of turns in the primary voltage, secondary voltage. So we can say that NS is equal to NP multiplied by Vs over Vp. Therefore, number of turns in the secondary would be equal to 4800 multiplied by the secondary voltage, that is 16, over the primary voltage, that is 240. So the number of turns on the secondary comes out to be 320. Moving on to question number 9. Figure 9.1 shows an electricity cable that has a fault, and the cable is used for supplying electricity at a high voltage. State the fault and describe the hazard. All right. The fault is basically, as can be clearly seen, there's a damaged insulation, you see, and the conductor is getting exposed. So the fault is damaged insulation, and the hazard is pretty obvious, could be electrocuted or electrical hazard. All right, moving on to part B of the question. Figure 9.2 shows a piece of cable used in a main circuit. State the name of wire X. So we have live wire labeled, neutral wire labeled. So wire X should definitely be the ground or the earth wire. All right. These are the two nomenclature used in literature. All right. For B subpart 2, an electrical appliance is connected to the main circuit. One of the wires in the cable is connected to the switch for the appliance. State and explain which wire is connected to the switch. All right. So the wire connected to the switch should be the live wire. Why? Why? Because switching on off should connect or disconnect the appliance with the main circuit. All right, that's pretty much. Uh, let's move on to question number 10. So we have, yes, 10A. U235, U238 are isotopes of uranium. Compare the number of protons in one nucleus of uranium with the other, with the number of protons in the one nucleus U238. Well, the protons remain the same, as can be seen here. Now compare the number of neutrons. All right, so here U238 has 3 more neutrons as compared to U235. That's it. Uh, for part B, a sample contains another isotope of uranium. The half-life is 24 minutes. Calculate the time taken for the mass of this isotope in the sample to decay from 16 milligram to 4 milligram. So the first thing we need to identify is how many half-lives are involved. So from 16 milligram for in one half-life, 16 milligram would drop to 8 milligram. That's one half-life. And then 8 milligram would drop to 4 milligram in the another one half-life. So we can say a total of two half-lives would decrease the mass of this particular isotope of uranium from 16 to 4 milligram. So two half-lives, that is 48 minutes. Moving on to question number 11. So table 11.1 shows some information about two of the planets in the solar system, the Venus and the Earth. So Venus is a similar size planet as compared to Earth, and state why the gravitational field strength at the surface of the Earth is greater than the gravitational field strength at the surface of Venus. So the gravitational field strength is basically inversely proportional to the mass. And since Earth has higher mass as compared to Venus, therefore, uh, the gravitational field strength at the surface of Earth is larger as compared to Venus. All right, part two, calculate the time in Earth days for one day on Venus. All right, so uh, from the table above, time for one rotation on its axis in hours is 5832 hours. That's pretty long days, right? So 5832 divided by 24 hours, which is one Earth day, would give you yes, that would give you the time in Earth days for one day on Venus. So 5832 divided by 24 gives us 243 Earth days. So so for one day on Venus to pass is equal to 243 Earth days. Yeah. All right. Moving on to sub part three of part A. Calculate the time taken for light to travel from Sun to Venus, and the speed of light is given. That is 3 times 10 to the power 8 meter per second. From the table above, we can see that the distance from Sun to Venus is 108.2 times 10 raised to the power 6 kilometers. So we can find the time uh, by dividing the distance, which is given, that is 108.2 multiplied by 10 to the power 6, but that is in kilometer. We need to convert that into meters. So multiplying again 10 to the power 3 for meters divided by the speed of light, that is 3 times 10 to the power 8 meter per second. Some meters will cancel out, and if we calculate that, it gives us 360.7 seconds. All right, moving on to part B. The star nearest to the sun is about 4.25 light years from the sun. All right, explain what is meant by one light year. So it's a pretty simple concept. One light year is the distance traveled by light in vacuum for 1 year. So we know the speed of light in vacuum, that is 3 times 10 to the power 8 meter per second. Multiply that with 1 year, so you would get the distance. And often these light years, these huge units are used for measuring these like absurdly large astronomical distances, because these kilometers, these miles, this sounds irrelevant and often futile while measuring the astronomical distances. All right, that's the end of the paper. I hope this proves to be helpful to all the viewers. Thank you so much.